Well, some people have a cool name. Some people have cool hair. Some people discover cool math concepts. Some people are La Hopital. Really, Google his name sometime. I don't even remember it, but it's so ridiculously long. It's a whole bunch of names. But the point of this is that there are a lot of things that we try to avoid. We try to avoid strangers in public. We try to avoid strangers in private. We also try to avoid things mathematically that we don't understand, that no one understands, like this. What is 0 divided by 0? People can argue it is 0 because the numerator is 0. They could argue it's 1 because anything over itself is 1, right? Not this. You could also argue that it's undefined because you've divided by 0. Because of that, we don't play this game. Also, infinity over infinity. Oh, that's just 1. Oh, is it now? Not necessarily. There are different sizes of infinity. And again, infinity, I've said this before, infinity is not a number, infinity is a concept. Negative infinity over positive infinity over negative infinity. There are lots of them. We could do negative infinity over negative infinity. The first two are the big ideas. There are a few other ones that are a little more obscure that don't happen as much, and they're just kind of fun to think about. See, wasn't that fun? I was thinking you didn't know what they were yet. 1 to the infinity, and that you're like, oh, that's just 1. Is it now? We don't know. Infinity minus infinity, oh, that's 0. Is it now? Different sizes of infinity. Here's a fun one. 0 times infinity. And then my own personal favorite that I actually have a little bit of frustration over is 0 to the 0. Because 0 to a power is 0. Anything to the 0 power is 1. And then 0 to the 0, well, what is it? Who knows? And there are some people, including Desmos, the people who've programmed Desmos, say this is 1. And as much as I respect them, I disagree. I believe it's indeterminate. Okay, here's the big idea though. The first two are the main two. And anytime we come across those two, we avoid them. And this guy helps us do so. I mean, just look at the dimple in his chin. You know, how could you not like the guy? So what we're going to do, bound to be a good mathematician with such a dimple, we're going to evaluate these limits, and we're going to use L'Hopital's rule, which is a very lengthy explanation of what to do. But here's what's going to happen. I want to kind of demonstrate what's really going on here. If we took the limit as x approaches -2 for the numerator, and I'm going to write it out because this is how it would need to be written on a free response question. We can plug a -2 in, we'd get 16. 16 minus 16 would give me 0. Yay, okay. We will plug in -2 into the denominator, evaluating that limit, and we would also get 0. Now, I know every bit of this could have happened in your head, but here's what we're not going to do. We are not, I repeat, not going to ever say that this equals 0 over 0. That is not true. Nothing equals 0 over 0 because we don't know what it is. What we just did was explain to the person who's grading our paper that we know that we end up with 0 over 0, but we never said it equals 0 over 0 because that's not a thing. Because it equals, notice the little quotes, 0 over 0, but not really, we have to use L'Hopital's rule. It's wordy, bear with me. F and G are functions that are differentiable on open interval a, b, containing c, except possibly at c itself. Okay, so there's some interval, and then we have some x value c, and the functions are differentiable, but maybe not at c. And we assume that the derivative of g is not equal to 0 for all the x values in a, b, maybe at c itself. Here's the big idea right here. All this kind of sets it up to make sure it works, and then we keep going. If the limit of f of x over g of x as x approaches c produces any of these, I listed a few more up here because these can be manipulated to turn into those. But if it produces any of these, then check this out. The limit as x approaches c of f over g is equal to the limit as x approaches c of f prime over g prime, provided the limit on the right side of the equation exists or is infinite. That'd be this guy over here. Okay, let's make sure that whole thing makes sense. Again, this first sentence is a fancy way of setting everything up just to make sure it works. If you don't get this, first two sentences. If you don't get those first two sentences, it's not going to mess you up in the process. So let's keep moving. If the limit produces any of those, then look where I'm pointing. Take the derivative of the numerator, take the derivative of the denominator, keep on working. That's the big idea. Because we got 0 over 0, we will use L'Hopital's rule, and we will take the derivative, still evaluating the limit, take the derivative of the numerator, take the derivative of the denominator, and go from there. Can we plug a -2 in for x? Yes. -16, done. Okay, now, back in the day, we used algebraic manipulation for this same problem. And in those notes, I said, there's another way. It's a fun little rule called L'Hopital's rule. And what we did was we would factor out that we had x squared minus 4 and then x plus 2. We were evaluating the limit as x approaches -2. And we got this, and then x plus 2 and x minus 2 over x plus 2, and we're still evaluating the limit as x approaches -2. My handwriting's sloppy. And then we plugged in a -2 right here, and we ended up with 4 times -2 minus 2, which gives me -16, and it works. And this is fun, but this is fast, and this doesn't always work. So let's keep going. Okay. Let's just do it in our head real fast, and then we'll explain to the person grading our paper that we know to use L'Hopital's rule. So the limit as x approaches infinity for the numerator is infinity. The limit as x approaches infinity for the denominator is infinity. We have infinity over infinity. We don't play that game. Thank you, L'Hopital. Let's keep moving. So because of that, and again, this might look like it's a waste of time, but I am demonstrating that it is necessary, or maybe not necessary, but expedient for us to use, applicable maybe, to use L'Hopital's rule because we have infinity over infinity. Now, let's be real honest. We did a lesson on this exact same thing where we would look at this and say, oh, the degrees are the same, so the answer is 2/3. Jump straight there if you want to, okay? If you want to, again, shortcut, 2/3, x squared. For infinity, who cares if you subtract 5 or add 2? Who cares? It doesn't matter. However, to demonstrate this with L'Hopital's rule, we would have infinity over infinity. That is forbidden. Let's take the derivative of the numerator and the denominator. You know, back in the day when you learned the quotient rule and you're like, can't I just take the derivative of the numerator, take the derivative of the denominator? Well, now's your chance. So it's the limit as x approaches infinity of 4x over 6x. And at this point, actually, you can just cancel your x's and you would be left with the limit as x approaches infinity of 4 over 6. I could have just put 2/3 there. Infinity, well, there's nowhere to plug it, so 2/3. Done. Okay? All right, let's keep moving. Let's keep the same color scheme going, too. If I plugged in a 0 here, I would have, well, the limit as x approaches 0 of e to the 2 times x, I don't know why I put parentheses there, minus 1 would equal, let's see, e to the 0 is 1, 1 minus 1, 0. Ooh, 0 in the numerator. We might have a situation like this. If we don't, we would just evaluate it like we would evaluate any other limit. Limit, x approaches 0 of e to the x minus 1. Plug in a 0. Oh, also 0. 0 over 0. We have to use L'Hopital's rule because it gives us 0 over 0. So let's move on with purple because that's what we've been doing. We will do L'Hopital's rule when you encounter 0 over 0, infinity over infinity, or any of the other ones, but these are the two biggie, like I said, two biggies. Too biggie. The denominator, derivative of e to the x is e to the x, minus 1 goes away. Derivative of e to the 2x is 2e to the 2x, minus 1 goes away. We can now plug a 0 in, right? Can we? Let's do it. So we will have 2e to the 2 times 0 over e to the 0, which gives me 2 times 1 over 1, which is 2. Done. Man, this is fun. Love this stuff. All right. If we plugged the negative 5 in the denominator, we'd be dividing by 0. If we plugged the negative 5 in the numerator, we would get 0. Let's demonstrate it for the people that are grading our paper. Man, this is a lot of writing. I know. I hate to lose points, though. It sure would be a shame if the guy or girl grading our paper didn't know that we know what we know because we didn't demonstrate it. Here we go. Oh, my goodness. La Hopital. Let's take the derivative. Take the derivative. I don't know where that accent came from. Let's take the derivative. A derivative of the denominator is 1. Things are going to work out well for us in this context. Derivative of the numerator. Okay, well, the derivative of a square root is 1 over 2 square root. And then we'd multiply, chain rule, times the derivative of 1. Multiply by the derivative of x plus 9, which is 1. And then that minus 2 goes away. So we are totally able now to plug a negative 5 in. So let's do 1 over 2 square root of negative 5 plus 9. It gives me 1 over 2 times the square root of 4. 1 over 2 times 2, which is 1/4. I like L'Hopital's rule, so practical.